See, BGP is one protocol, but it is in two different form, I can say. Meaning, if you take EIGRP, it's one protocol, but you can see there are two administrative distance, 90 and 170. Internal EIGRP, external EIGRP, but basically it's one protocol. Whenever we redistribute routes from outside, we call it as external EIGRP, whose administrative distance is 170. For those networks that are advertised locally, it is only 90. Likewise, those routes that are given by eBGP are called as eBGP routes. Those routes that are given by eBGP. Who is eBGP? The peer who belong to different autonomous system is an eBGP. The routes that are given to us by our remote peer who belong to different autonomous system, we call it as eBGP routes, external routes. Same route, when our edge router provides to our inside router, it's IBGP given route. Even though it's an external route, it's IBGP given route. Because we call these two routers that belong to same AS as IBGP. This relationship between 2 and 3, we call it as eBGP. So the routes that are coming from here, alpha, 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 when it comes to router 1, even though it is coming from remote autonomous system, it is given by our IBGP neighbor, IBGP given routes. Basically, they are not belong to our own autonomous system. They come from very far remote different autonomous system. So when R2 gives, they are seen as IBGP route, for which administrative distance is 200. Same alpha when when 3 gives to 2, when 3 gives to 2, same alpha administrative distance is only 20. So this is one big difference between eBGP and IBGP. But again, I told you in the previous class, this difference is only in Cisco. In Juniper, the administrative distance is same for both IBGP and eBGP. The administrative distance is same for Juniper, it's 170. They call it as preference value, route preference. Now, coming to Cisco. So there is definitely some difference in this flavors of BGP. That's why Cisco wants to differentiate with the administrative distance. You see, they have given more importance to eBGP learned routes. 20. No routing protocol is having this small number. The smallest number that we have is for EIGRP, which is 90. Smaller the number, more preference is given to those routes. So there will be a reason behind why we have this 20 and 200. We are going to see that. But protocol is not two. Protocol is only one, BGP. Even you saw in the configuration, the commands are same for both IBGP peering and EBGP peering. Only the autonomous system number that makes difference, that tells the router whether it is an EBGP peer or IBGP peer. What is BGP peer neighbors? If BGP can finish that three-way handshake successfully with someone, repeating again, if BGP can complete the three-way handshake with a router, then it is possible to easily establish a connection. Three-way handshake will not complete if the constraint, like source address of the sender, should match with the neighbor statement. Only when those matches, the TCP three-way handshake for port number 179 will be complete. That's why it is said here, who is a BGP peer? Any two router that has formed the TCP connection to exchange BGP routing information are called as BGP peer or BGP neighbors. As we saw, one of the flavor is external BGP, whose administrative distance is 20 for those routes that are learned. See, this is the constraint. EBGP neighbor by default need to be directly connected. EBGP neighbor by default need to be directly connected. To achieve this, the TTL is set to 1, and you saw that in the previous lab session. Now, why it is that important? Why is that TTL value 1 set by default? Security. You might have heard about BGP Hacked. Maybe a week before, you might have heard or read somewhere. BGP Hacked. Hijacked. BGP hijacked. That's the word. BGP hijacked. What is it exactly? Somewhere in the big ISP, wrong routes has been injected. Wrong routes are injected. Wrong routes are injected. It is because the router formed neighbor with a spoofed peer. Very simple, right? If I want to form neighbor with a router, I need to be in the same subnet. And I need to have an IP address which is configured as a, which is already configured as a neighbor. Let me put it easy. You see here, the neighbor is 1.1.1.1 configured. Autonomous system is 65100. This is what configured on C router. Anyone whose IP address here is 1.1.1.1 and who claims to be 65100 can form neighborship. Correct? They can form neighborship. Easy. So someone who wants to hijack, all that they need to know is the IP address that is mentioned as a neighbor and the autonomous system number that is mentioned with the neighbor. So someone did this and they formed neighbor with one of the ISP and they might have given invalid route, or they might have routed all the traffic through their own network so that they can go through all the packets that transits. I don't know, it is my guess. I did not read in depth what really happened. I just read the word BGP hijack. Then I was laughing, I was smiling inside, okay, this is what would have happened. I did not read the content. See, to avoid such hijacks, eBGP neighbors need to be directly connected. If it is directly connected, then to an extent you have security. That also, people can spoof but when we form neighbor with the remote router, it is very difficult to trace if someone spoofs. Just one hop away, it is easy to trace. How can we prevent such BGP hijack? This is one of the technique. Do not change this default. Neighbors need to be directly connected constraint. Don't change it. If you change it, make sure you don't send the BGP packets to a far distance. Try to keep it as low as possible, like 2 hops or maximum 4 hops. In Huawei, if you forget to say how many hops, meaning by default in every vendor device, eBGP need to be directly connected. But if you try to change it, in Cisco also we can change it by using a command eBGP multi-hop. You can put 2 to override this rule. But in Huawei, if you don't specify the number of hops, it will take it as 8 hops. So within that 8 hops, if there is an attacker, then we are done. That's not the way we should configure this type of sensitive things. So we need to be very particular in number, how many hops. All right, so BGP is running between neighbor that belong to different autonomous system is called as eBGP. eBGP neighbor by default need to be directly connected, but if you want to override this, you may do it by using a command eBGP multi-hop, and then you can say hop, how many hops, 2 hops, 3 hops. If you say 3, the TTL will become 3. Unless there is some good reason, you should not do that. We will see one such reason why I need to increase the TTL value after some time. When I form neighbor within same autonomous system, we call it as IBGP. For this, neighbor do not have to be directly connected, and you saw the reason. The TTL was 255. Next. This is going to be some serious topic now. Next 3 pages needs your close attention. This one and next 2 pages, because it teaches some very important fundamental. This one, what you see here, very clearly says that don't redistribute. Instead, run IBGP on all router. See, to avoid black hole, to avoid black hole on these routers. 2 ways you can solve it. One, run BGP on all routers, or redistribute. But redistribute should not be an option for us. You see, there's a network called 1.1.1.1 coming as an advertisement. From here, 2 is coming. B and E or IBGP neighbor, you see, the dotted line, what does it say? It says these two are neighbors. There's no physical wire. There is no physical connection between B and E. There is no direct physical connection. B is forming neighbor with E via D or C. Using D or C as the path, it forms neighbor. You see, there is a OSPF routing protocol running. So using OSPF, B can ping E. If B can ping E, we just learned that they do not have to be directly connected. IBGP do not have to be directly connected. So they form neighbor. B formed neighbor. So it advertised to E about 1.1.1.1. Likewise, E advertised about 2.2.2.2. Now 2.2.2.2 is learned in the BGP table here. 1.1.1.1 is learned in the BGP table here. Now when you try pinging, what happens? The packet comes up to E and then drops. Why? D is not a gateway for that network. B is the only known gateway. When it tries to send it to B, it is only via D it can reach B. So when it goes to D don't know about 2.2.2.2 and 1.1.1.1. D has got no idea about these destinations. That's what we call as black hole. Black hole occurs because of different reasons. One, late convergence. Two, like this, BGP is not properly configured. Three, loop summarization, improper summarization. Yes, please. Exactly. D and C don't have any route about any information about 1.1.1.1 and 2.2.2.2. Yeah, 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 yeah. Yes. So BGP can give the routes to E because it's TCP, updates are TCP. B will directly deliver it to E. Likewise, E will directly deliver to B. Even though the path taken is via D, D will not know about it because it's just a TCP packet delivered. BGP, when it sends update, it will send it to neighbor. Who is neighbor? E. It puts E's address and send to D. D knows where is E because you run OSPF. It delivers the packet to E. E synchronizes its table. But you will not see D getting synchronized because D will not even open the packet. D's job is to simply route the update packet to E. So D is not going to have route in the routing table. As a result, packet cannot go. Even though F knows about A route, A network, A knows about F network, because the transit router in the middle, D and C don't know, the packet drops. To avoid this packet drop, most of them does this problem, a mistake, they redistribute. They take the BGP route and translate to OSPF, and again here they take from OSPF, put it into BGP, which is not recommended. Why it is not recommended? I'll give you two reasons. Number one, when I take it from BGP and put it into OSPF, BGP has got a lot of attributes attached to each prefix, each network, each route. A lot of attributes attached to it. And I showed you yesterday in the capture, like local AS number, like local preference value, origin, and then MED, and then AS path attribute. Likewise, you saw a lot of attributes attached to every prefix. And when I take that BGP update with a lot of attributes and redistribute into OSPF, who knows only cost? All your attributes are lost. And it comes as a simple route with metric cost. So the purpose of enabling BGP is gone. Because all the attributes are now forgotten. It's only OSPF metric cost is given to those prefixes that are coming from outside. And now when I redistribute back from OSPF to BGP, all those attributes that were set here on F is gone. For example, when I receive the packet from F to update from F, not packet, update. When I receive this 2222, I'll see only one thing. What? It is coming from autonomous system 65102. That's all. I will not be seeing the original originator from where the route originated. I will not be seeing 65103 at all. Why? When I took from BGP and gave to OSPF, all those attributes gone. Yes, path is one of the attribute. It is gone. OSPF don't understand those attributes. Then this type of routes cannot be used for loop prevention, because based on AS number only loop is prevented. In the public, this type of redistribution will spoil the entire internet. Loop will occur. No one will know from where it really originated. No attribute, then no use of BGP. So, this is one of the reasons why I should not redistribute. The second reason is, when I take from OSPF and give it to BGP, not only the F routes are getting redistributed, even my internal networks, my private networks, which was only with OSPF, now shown to the public. Public will know about my inside networks now. Because OSPF is not just for external network, it's for internal network. OSPF is taking care of my all inside networks. So when I mix BGP to with OSPF, the external, internal, everything get mixed. And when I redistribute back from OSPF to BGP, along with F routers network, E, C, D, B routers network also get advertised, which is not safe, not acceptable also. Then you may write a lot of route filtering. You may write distribution list and filter all your inside network. These are all extra work. Again, even if you do like that, the purpose of we enabling BGP is lost. All the attribute is gone. So redistribution is not at all a solution. Are you convinced? We must write BGP, we must configure BGP on all the routers. Yep. Now, I would like to skip one page and go to the third page, and then I'll take you back to second page. Skipping one, two. Now you see this page and check whether you understand this. We have covered this. Going back to the previous page, we decided to have BGP on all router. But in the production, are we do that? Are we doing it? Are we going to use this as a solution? No. So I'm not going to explain you now. Let me explain you something and then come back again. In production, what we do is, this is actually a service provider, right? They run MPLS tunnel. Problem solved. All the routes come in, get encapsulated and goes to the other end and goes out. No need of BGP here. And the packet won't get dropped. Because it is encapsulated with source address E, destination address B, which is known to D, and D routes the packet. That's what called as tunnel, right? Layer 3 MPBGP I'm talking about. So that is the best solution, having MPLS layer 3 VPN between B and E. So DNC router, when they process the packet, they will not be sending to a destination D, because that is encapsulated with the source address of E and destination address of B. So according to D, it thinks that it is forwarding the packet to B. It processes only B as the destination address when you have tunnel between E and B. And when B receives the packet, it decapsulates and it finds the original destination. The original destination is 10 network and it delivers to A router. This is the solution, but not BGP solution, no? It's BGP with MPLS. So the BGP solution is this. Only BGP, no MPLS. You need to have BGP on all routers. Let me go back and then bring you again. So we have decided to run BGP on all routers. Running on all router needs to be full mesh, is what this page explains. Running on all router, partial mesh is not enough. What does that mean? Let us explain. Let us learn through a paint. Same diagram I am drawing. Router A is advertising this 2222. It goes to B. Now, what is said here is partial mesh. Let's see what is the problem with partial mesh. Why we need, see, we need full mesh. We'll understand why we need full mesh. What is partial mesh? B forming neighbor with C and D. That's all. B is not forming neighbor with whom? With E. B only forms neighbor with directly connected. Likewise, C forms neighbor with B and E. D forms neighbor with B and E, and vice versa. So what we see here is the routers form neighbor only with the adjacent routers, not with all the routers. That's what explained in this tiny picture. See, there is no IBGP. See, BGP is running on all router, but the neighborship, the neighbors are not with all the routers like this. See here, B has got dotted lines with the D, which is IBGP relationship. It also has got a dotted line with E. You see the arrow mark? The dotted lines. Means if I have 100 router, then I need to form 99 neighbors. Here we got 4 router, so 3 neighbors each. Means I mean IBGP neighbor. Just IBGP neighbor alone, 3 IBGP neighbor on each router, which is what called as full mesh. Forming neighbor like this only with the directly connected is not full mesh. Partial mesh. Partial mesh is not sufficient. Are we running BGP on all router? Yes. We found that we need to run BGP on all router, OSPF on all router, already running IGP protocol. Now we decided to run BGP on all router, but when you run BGP on all router, we need to form neighbor with every other router, not just the directly connected. That's what we are trying to learn. Why? We need to form neighbor with every router. Why should BGP neighbor with E? Why with C and D is not enough? To understand that, I would like you to see another topology. See this topology. I'm going to redraw it. Instead of these connections, I have a switch in the middle. Let's assume. I got switch. Now, an update is coming. This 222 is coming. So I'll just put one dot. The dot comes here and this gives to everyone. C has received it, E has received it, D has received it. Now for C, If all others are neighbor, what C will do? Whatever it received, it will send to other two neighbors. C received it from B. Now C sends whatever it received to D and E. Now for D and E it becomes a duplicate. Same way, whatever E received, it is sending to C and D. Again it becomes a duplicate. This is going to cause loop. Likewise, it will be keep on repeating. Everyone will be sending the same thing again. How can we stop this? They have solved this problem by a rule called IBGP split horizon rule. What does it say? When you learn this 2.2.2.2 from an IBGP, is BGP IBGP or EBGP to C, D and E? It's IBGP. B is an IBGP to C, D and E. The rule is, if you are learning from an IBGP, do not give it to another IBGP. So E can give it to F because it is EBGP, but C cannot give it to E because it is IBGP. Route learned from an IBGP should not be given to another IBGP. Should not be given to another IBGP. That solves the problem. Look at this. By default, the route learned via IBGP are never propagated to other IBGP peer. So what? Now going back to this. Route learned from an IBGP are never propagated to another IBGP. As a result, E won't be learning about 22222. Likewise, B will not be learning about 11111. Then how E can learn 2222? You form adjacency so that using TCP, it will give directly to E1 copy. Like we saw in this previous scenario here. This will give directly the route, like you saw here. The network 10 is learned on F. How? A gave to B, B gave directly to E, and E gave to F. There's a black hole. So if you are making full mesh, you need to form full adjacency. Sorry, if you are making, if you're running BGP on all router, you need to make full mesh. That's the moral. That's the end of the story. Please ask me question. Yeah. No. Yeah, your statement is right. But the first statement, what you said, route learned from an EBGP will be given to IBGP, but route learned from an IBGP won't be given to another IBGP. That's what I meant. So this 1.1.1.1 comes to be now, which is route learned from a EBGP. Route learned from an EBGP can be given to an IBGP. There is no problem. So D will also learn about 1.1.1.1 now. But according to D, who is B? IBGP. According to D, B is IBGP. So that 1.1.1.1 that D has learned from an IBGP, it will not give it to E. It will not give to E. It won't give it to E. So what we do is we tell BGP on B router to give it to E directly. As it gives to D, it will also give a copy to E. Is that same thing you understood? Wonderful. So we have learned that BGP needs to be on all the routers in the transit, and also to override this IBGP split horizon rule. No, we are not overriding. The rule is still there. In order to have the routes in all the routers, I need to have adjacency with every IBGP router. As I said earlier, if I have 100 IBGP routers, I should have 99 IBGP neighbor. Now you may think like, what? 99? So when one small update comes, we need to duplicate it 99 times and send to 99 IBGP neighbor. Yeah, that's the bitter side. 99 times you're going to duplicate and send to 99 different neighbor. What is the problem there? Bandwidth utilization is high. Because BGP updates are not small updates. They come with a lot of attributes. Plus, the process utilization is also too much. B has to duplicate it 99 times, more processor, more RAM, memory. And every now and then when there is a change, this repeats. Duplication, sending, all process it. So even that is also not a solution. This is a solution that will work, but not a scalable solution. What is a scalable solution then? As I said earlier, we need to form a tunnel between B and E if one minute please. We need to form tunnel between A and B if we are not allowed to do a physical connectivity. If I am not able to do physical connection to B and E, see, if I have physical connection to B and E, I no need to run BGP here. You have physical connection directly, you give, no problem. But if you are not having that option, at least a tunnel you put. Even if it is GRE tunnel, it will work. So BGP will be running here and then on GRE and then on this interface and then it goes. You don't need MPLS. MPLS is the best one. GRE can also be used. People use GRE. People use DMVPN to do this. Many runs BGP on DMVPN for this reason. But MPLS is the recommended. MPLS, MPBGP layer 3 tunnel, which is not explained in this presentation because those things are not part of BGP. So in this chapter, we learned what BGP Peer means and the difference between IBGP and eBGP. We learned that eBGP neighbors need to be directly connected. IBGP neighbors do not need to be directly connected. And then we learned that IBGP neighbors are routed in the same autonomous system that are reachable via OSPF or via static routes. So we need to make sure we need to run IBGP on all the routers so that the routes, the external routes will reflect in the IBGP routers and there won't be a black hole. And when you run IBGP, also try to have full mesh, not try to have, we must have a full mesh. Otherwise, the IBGP split horizon rule that prevents a duplication of update, which is route learned from an IBGP should not be propagated to other IBGP, will be a problem if you don't make it as full mesh. Solution apart from BGP is having MPBGP, form a tunnel so that you don't need to run BGP on every router. Listen, 100 routers running BGP, that's too much. If I have tunnel, just 2 routers will run BGP. See, big advantage. If I have tunnel between B and E, 2 provider edge routers that connects customer, I no need to have 98 routers. Only OSPF they will run. See how much process you save, how much the network efficiency will be improved if you avoid BGP. BGP is heavy, BGP is too heavy. We cannot run BGP on all the routers. The performance will go really down. If there are ISR routers, CSR routers, it's okay. But normal iOS router carrying those big updates, processing them, maintaining them, not that scalable. Forming tunnel will be the best solution. When we go MPLS class, we'll learn these things. Right? As of now, we'll stop here. We'll get into the next chapter.